Hello, everyone. Welcome to Wolfram R&D Live. My name is Robert Feger, and it is my pleasure to talk about LieART for algebras and representation theory in the Wolfram language. LieART was developed by me together with Tom Kephart and Robert Saskowski. So LieART is just short for algebras and representation theory. And LieART brings algebras and the representations to the Wolfram language. LieART provides a lot of basic properties about algebras, such like simple roots, the root system, the Weyl group with its orbits and chambers in the root system. And it also gives you a lot of information about Lie algebra classification, especially it can plot Dynkin diagrams. It can also give you a lot of information about irreducible representations of Lie algebras, which includes weights and weight systems, Dynkin labels for labeling the irreducible representations and the dimensional name, as well as a Young tableau correspondence. LieART also computes tensor product decomposition and subalgebra branching of irreducible representations. And this was the main purpose for building this package, because this is frequently needed, especially in particle physics, where I needed it for. LieART is open source, and you can download it from HepForge. This here is the link. I will pull that up at the end as well. And you can also find installation instructions on that web page. Once you have it installed, you can just load the package in Mathematica by loading its context. So let me give you a bit of theory about Lie algebras, and I will use LieART along later on to demonstrate what it can all do. So what are Lie algebras? Lie algebras can be described as infinitesimal Lie groups. So what are Lie groups? Lie groups describe continuous symmetry transformations. So when you have a symmetry and you do a transformation along the symmetry, nothing should change. I have here two examples. On the left side, you see a hexagon. And here I can modify the rotation angle and can rotate it. And you see something changes. So there's no symmetry according to this rotation. But if I rotate from this here to 60 degrees, to 60 degrees, then I will retain the same hexagon. And every 60 degrees, it will look the same. This is then not a continuous symmetry, but it is a discrete symmetry. On the right-hand side, you see a circle, and a circle has a rotation symmetry. And you can see that by rotating it by an arbitrary angle, and you will see nothing changes. So that's a continuous symmetry, and that can be described by a Lie algebra. Well, by a Lie group first. So in 3D, the 3D rotation group is the group of 3x3 orthogonal matrices with a determinant +1. And it's called the special orthogonal Lie group SO3. So now we will look at a small rotation by phi about the z-axis. I'm using small because I said something about infinitesimal Lie group. So here, this is a rotation matrix. You can even find that in Mathematica with sine and cosine. And since the angle is small, you can approximate the cosine by 1 and the sine by phi, and you end up with this matrix. You can then decompose this matrix into the identity matrix and another constant matrix called Tz, which I wrote here on the right-hand side. Essentially, you can pull out the angle phi, which is very convenient. So this constant matrix Tz is a so-called generator. And the nice thing about this generator is you can express the finite rotation with it. So here you see by exponentiating this term up here, you retain the whole transformation for the finite rotation. Essentially, this term up here is just the Taylor expansion of this exponential here up to the linear term. So in the same way, we can find the other generators of the rotation in 3D. So the rotations about the other axis. So this is Tx and this is Ty. These three, Tx, Ty, and Tz, they form the three-dimensional representation of the special orthogonal Lie algebra SO3. So this is not the group, this is now the algebra. The Lie group, they have an infinite number of elements, which is due to this parameter phi. And the advantage of the Lie algebra now, instead of the Lie group, is that you can get rid of this parameter, and you don't have infinite number of elements, but you have a finite number of elements, and you can study that instead of the group. But then you get a lot of properties of the Lie algebra, and a lot of these properties can be transferred to the Lie group. So I said that these generators that I just showed you, the matrices, they are a representation of the generators of SO3, and they obey these commutation relations. So this is the commutator of these two matrices, and they are linear to TZ, and then there are the same commutation relations for all the other combinations. Now, instead of talking about matrices and representations, you can discuss an abstract Lie algebras. And in an abstract Lie algebra, you have generators Ti, now not with a capital T, but with a small t, and they obey the so-called Lie bracket. This here is the Lie bracket. The Lie bracket looks like the commutator, but it is a general operation, which is an alternating bilinear operation, which satisfies the Jacobi identity. As these elements Ti are abstract, it's not necessarily the commutator. It's only the commutator when you use a representation. Here, it's just this operator with these properties. And if you're using a representation, that can be matrices, that can be the commutator, but it can also be the cross product if you, for example, use vectors. And so here you have these so-called structure constants appearing, and how they are fully describes the Lie algebra that you're using. And now what's the difference between the abstract algebra and the representation of the algebra? The representation is a linear map of the Lie algebra into the matrix group. And the matrices that you use in this map, they must obey the same commutation relations as the algebra. Then they are a representation of the Lie group. Algebra, sorry. So I told you about the structure constants. There are many of these structure constants, and it can get even easier than that. So you can use what is called root, which is a subset of the structure constants. For that, I need to introduce the Cartan subalgebra. Some of the generators, so the small TIs, they are called HI, and they belong to the so-called Cartan subalgebra, and they are simultaneously diagonalizable, and they're Hermitian, and so they mutually commute. That means the structure constants for them are 0. I wrote that down here. This is the commutator or the Lie bracket of the generators, and it's all 0. And there's only a certain number of these generators, which is n, and this is also called the rank of the algebra, of the Lie algebra. So now you can do the Lie bracket with all the other generators and these special generators of the Cartan subalgebra, which I wrote here, and they have some subset of these structure constants, and they are exactly n ones, so as the rank of the algebra, and you can use them to label the other generators, so the TJs in these equations. And these n structure constants, AI, form the so-called root vector alpha of TJ, which I wrote down here in the general form. And the term root stems from the fact that the root vector is the solution to this eigenu equation. The root vectors, or simply roots, they label the generators of the Lie algebra, and even the same is true for the Cartan subalgebra, where they are all 0 because of this here. Root vectors, they lie in an n-dimensional Euclidean space, which is called the root space, and there are different choices of bases for them possible. I give you an example. This is the special unitary group SU3. We use the special orthogonal group SO3. This is now the group of the unitary matrices. So in general, this is something like a complex rotation. And They're quite popular in physics, especially in particle physics, where they are all used all over the place, especially in the standard model. And there's standard basis for the representation of the SU3 in particle physics, which stem from Gell-Mann, and they are also called by him the Gell-Mann matrices. There are 8 of them, usually labeled by lambda 1 to lambda 8. I wrote them down here. And there's the convention for the SU3 generators that they are half the Gell-Mann matrices. So you see in the Gell-Mann matrices, lambda 3 here is diagonal, and also lambda 8 is a diagonal matrix. That means they mutually commute, and these are exactly the generators or the representations of the generators that you can put into the Cartan algebra. So here you identify the first generator of the Cartan algebra with T3, and the second one with T8. This is wrong. This should be T8. So we have 2 of them. That means the rank of SU3 is 2. And this here is the first command that we use from LieArT, which gives you the rank of SU3. Simple roots. So they are the roots. I introduced them, and there are some of these roots can be written in terms of others, but there are some of them for which this is not possible, and these are called simple roots. So basically, you can use the simple roots to generate all the others out of the simple roots. And the LieArT has as many simple roots as its rank, and they also fully determine the LieArT, like the structure functions, but there are much less information in them, but still this is enough to generate all of the algebra. I'd like to introduce to you the Dynkin labels. The Dynkin labels have this definition here. So this here is a scalar product in this space. Alpha is now a general root vector. Alpha I here is now a simple root that I just introduced. This here is a scalar product of the simple roots by itself. So it's basically the length of the simple root and with a factor of 2. And this Dynkin label is indicated by an A, not an alpha. It looks quite similar, but this is an AI. And the nice thing about the Dynkin labels is they are integers for all the simple roots. So it's easy to work with them. So the Dynkin, if you use the Dynkin labels instead of the root vector that I showed before, this is also called the Dynkin basis or the omega basis, and it is usually in textbook displayed by a framed box. I put that up here. And also LieArT is using this kind of visualization. So you can get the simple roots of SU3 with this command, omega simple roots, and it will give you the simple roots in the omega basis or in the Dynkin basis. And it looks like this. So these are the 2 simple roots of SU3. These are the Dynkin labels, 2 and -1 for the first one, and -1 and 2 for the second one. Some of you might know the Cartan matrix for Lie-algebras. And in fact, the Cartan matrix is defined in this way, which looks very much like the Dynkin basis, the Dynkin labels. And in fact, it turns out that the rows of the Cartan matrix are just the simple roots in the Dynkin basis. So here you see, this is the first simple root, this is the second simple root. So the root system. LieArT can provide the complete root system of LieAlgebra, and I will show you how it is generated in LieArT. This is the command for obtaining the root system of SU3, and there's an option to show it in a spindle shape, which is very nice, and I can explain a few things about it. So these are all the roots of SU3, and here you see 0 roots. These are the 2 roots of the Cartan subalgebra, because I said that the structure functions for them are 0, so are the Dynkin labels, and this is the Cartan subalgebra with a twofold degeneracy. The simple roots are here, just a row above the Cartan subalgebra, and all the other roots can be constructed from the simple roots. You can also display the roots because now we have 2 dimensions in SU3, which is very nice because I can show you a few plots about them. We need to go to a representation to show this and to show a representation of the Cartan generators, now H1 and H2 with a capital H. And we can use the adjoint representation for displaying the roots. This is specialty because the adjoint representation is the representation of the structure functions. That shouldn't bother you right now, but we can use it to show the roots in this space. So here you see the two zero roots here, and they are indicated by a dot and a circle showing that there are two, so the degeneracy of two, and the blue ones are all the other roots. And the simple roots, oh no, the next thing is the non-zero roots are often also displayed as arrows in that representation. So oftentimes, for example, when you pull up Wikipedia, you see plots like this. The two simple roots, these are all roots up here, and the two simple roots are these two roots here, and they come at an angle of 120 degrees. That will be important later on for Dynkin diagrams. Weyl group orbit. There's a so-called Weyl group, which is a reflection group, which is inherent in the root system of all simple Lie algebras. So the Weyl group is doing a reflection, and let me explain to you how this reflection works. This is a transformation Ri, which reflects a vector x at the hyperplane, which is orthogonal to the simple roots alpha I. So look at this picture here. You have the first simple root of SU3 here, alpha 1. You have the vector x here. I hope you can see my mouse pointer. And you have this hyperplane, which is now here just a line, which is orthogonal to alpha 1. This is the dashed line here. And basically what this Weyl group is doing is it's doing a mirroring of x at this hyperplane, and which results in the vector here on the right side. And you can see that here because this scalar product here is basically the projection of x on the simple root, and then this together with the denominator here is just the unit vector in the direction of the simple root, and you subtract it 2 times from x, which results in this vector over here. Then you can do this several times. You have now a new vector, and then you can even use this vector to reflect other vectors on the hyperplane, which is orthogonal to this vector. And you do that in a nested fashion. And in the end, it turns out you have a collection of vectors, which looks like this here. And this is the so-called orbit of x. And you might now remember, this is exactly the root system of SU3. So this is the way how you can generate the root system of SU3. So if you take any simple root of SU3 as x, which can be done here with omega simple roots of SU3, and we just take the first one, this is our vector x, and we reflect it using the command orbit, then we obtain these roots for the orbit. And now we include the 2 zero roots of the Cartan subalgebra, which are just here. There's even a command for generating them. This in total yields the root system of SU3. So if you compare what's written down here, yes, I can select it. If you compare this with the orbit and with the zero roots together, it's the same, even though the ordering is different. The Weyl group of SU3 is the symmetry group of the equilateral triangle, which I wrote down here, so you can see all the root vectors. You can see the hyperplanes to all of the root vectors. And I put in the equilateral triangle, and you can see you can flip or mirror the triangle at these hyperplanes. And the nice thing about this picture is now we started with a continuous symmetry, but now in the root system, we are discussing a discrete symmetry in the root system, which is much easier than discussing the continuous symmetry. Okay, let me move on. Weyl chambers. So these hyperplanes, they divide the space into the Weyl chamber. And I highlighted one of the chambers here. And the interesting thing about this is that in a single orbit, you have only one element per Weyl chamber. And the one that I highlighted here, this is called the dominant chamber, because the elements in the dominant chamber have only positive entries in the Dynkin labels, which is shaded here in gray in the omega basis or the Dynkin basis. So the dominant root is usually used, later on it will also be the dominant weight, is used to label the whole orbit. So let's see how this works. We build up the orbit out of one of the simple roots again, and then we select the dominant root out of this orbit. And you see here, this is the dominant root, and it has only positive entries. This is in fact it's the only one that has the only positive entries. And this is a very nice property because you can use just the dominant weights, dominant roots, instead of having all of them. And in the end, you're just building the orbit out of that. Okay, let's continue. Classification of Lie algebras. So when you study all possible root systems, it turns out that there's only a limited number, and Cartan did that. And he found out that there are two types. There are the classical Lie algebras and the exceptional Lie algebras, and he labeled them in the Cartan labeling with A, B, C, D, E, F, and G. And the classical ones they're also so-called infinite series because they come at arbitrary rank. So you can have the A, you can have an A2, A3, A4, and so on. It's infinite. But the exceptionals, they have fixed rank. You have E6, E7, E8, and that's it. And you have F4 and G2. So they are the traditional names. We used SU3, and as you can see here, SU3 is also called A2 in the Cartan labeling. Then the SOs, it depends on whether the dimension of the special orthogonal algebras are odd or even, and then they are either B's or D's. And there's also the symplectic algebra, which are the C's, or they are indicated by SP. So how to enter the Lie algebras? Internally, the Lie algebras are represented by this head, this combined head of algebra, with the algebra class here, A, B, C, D, and the rank, which is A2. This is now for SU3. In standard form, the Cartan classification is printed, so A sub 2. In traditional form, the conventional name is used, so the SU3 that we used all the time right now. And there are short forms that I predefined up to a rank of dimension 30. Here I have some examples. A12, for example, then turns into SU13. B18 turns into SO37, for example, because traditional form is the default output in Lie algebra. Exceptional algebras, they have just one way to specify them. They are just E6, E7, E8, F4, and G2. And they are usually just labeled this way, so there's no other traditional name than the Cartan label. Dynkin diagrams. Dynkin diagrams are very nice in depicting the length and angles of simple roots, and you can even derive the simple roots from the Dynkin diagram or the other way around. So in the Dynkin diagram, you use a dot, an unfilled dot, for a default length of a simple root, or a filled dot for a longer root, if longer roots appear in the simple root system. Then you use no line for connecting the dots for 90 degrees between the simple roots, one line for 120 degrees, two for 135, and three for 150 degrees. So for SU3, I showed you that the two simple roots have both the same length, and they come at an angle of 120 degrees. So this is the Dynkin diagram for them. You have just two unfilled dots because they have both the same length, and they're connected by a line because there is an angle of 120 degrees between them. Here are some other examples. This is the Dynkin diagram for SU5. So this is A4, which means it has a rank 4, and it has four dots that are all connected by one line. Then we have a Dynkin diagram for SO11, and here you have a root which is longer, so it's a filled dot, and you have a different angle between the fourth and the fifth root, which is 135 degrees. Here I have collected some of the plots, an example for each of the algebra types. So SU6 is an A, is an A5, SO11 is here. The symplectic groups, this is one of the examples, and the exceptional groups up here. And here you have another example in G2. You have even the angle of 150 degrees between the two simple roots. Representation. As I said before, representation is a set of matrices that represent the generators of a Lie algebra, and they need to satisfy the same commutation relations as the algebra. So this is here now the commutator of the matrices, and it has to come out, the same structure functions have to come out of these commutators. These matrices act on a space. For example, it's a Hilbert space that they act on. So they can be used in quantum physics, for example. And each vector in this Hilbert space can be labeled by eigenvalues of these diagonal matrices. So those matrices that represent the Cartan subalgebra, which I showed here. So this is a representation of a Cartan generator, and this here is a state. So this is in quantum physics the usual way of labeling a state by the bracket notation. This is a ket from the LieART notation, and even within the bracket you usually write the labeling of the state, which is exactly what comes out in this eigenvalue equation that is written here. So then an example in SU2, not SU3, now it's SU2. This has rank 1, and it has only one Cartan generator, J3. You usually write it down this way. So J3 is this Cartan generator, and this labels the state. For example, you use it with spin states or angular momentum states. J can label the representation that is in. For this representation, you only need just one number. And M is then the eigenvalue with respect to this Cartan generator. So this is what comes out here. So in general, you get n eigenvalues, lambda I, and they form the so-called weight vector, or simply the weight of this representation. You see a lot of things are very simple, are very similar to roots. So this is the weight vector which lives in an n-dimensional space, and this is also the same space as the root space. The dimension of the representation is the dimension of the space on which it acts, and it's equal to the number of weights, which is very important. The number of weights shows that this is a discrete points in this root space that stand for the weights. So the weights are linear combinations of the simple roots, and they're also expressed with the Dynkin labels. So here's the same definition. We had the same definition here with a root vector. Now this is a weight vector, and we also get these labels. And here it's the same as before. It's only integers, so it's very easy to work with them. So it's also, for the weights, it's also displayed with the framed box. So as I said before, the weights are similar to the roots. They are linear combinations of the roots. So many properties of the roots translates to the weights. So this here is the weight system of the 8-dimensional representation, which is the adjoint representation, which I already mentioned to you. And it is in fact identical to the root system of SU3. So every irreducible representation, which I will from now on call IRAP for short, has a unique highest weight, which has only positive Dynkin labels. So we had positive Dynkin labels for the dominant weight, and it has something to do with that. So the highest weight labels the IRAP in total, and usually this is denoted by this capital lambda here. And this is also called the Dynkin label of the irreducible representation. So usually it's written this way, but when these Dynkin labels, the individual Dynkin labels are just single-digit numbers, then the comma is left out. So this is usually the way the Dynkin labels is written for a representation. And this is even the same thing in LieART. So you can enter a representation by using this. You need this head, IRAP, of A for something with SU, for example, and then the Dynkin label comes here. You don't need to specify here that it is SU3 because it's clear from the number of Dynkin labels here that it is SU3. So the A is enough, and then in standard form it will display the Dynkin label here. The number of weights is the dimension of the IRAP And internally, this is computed by the Weyl dimension formula, and there's a command for getting the dimension of the representation, which is simply dim. And there's instead of the Dynkin label, like here, the dimensional name is usually used in, for example, especially in physics, which is output here in traditional form in boldface. So this representation in traditional form, which is the default, is then output as a boldface 8. And this can also be entered. So here you can enter it by just saying the dimensional name of the era, but here you have to specify that it's SU3 because they are 8-dimensional representation in other Lie algebras as well. So this is not unique. Here you need that. So there are some representations which have the same dimension as others, and especially for complex representations, you have one which is related. You have here, for example, you have the triplet of SU3, which is the 3 of SU3, and you have the complex conjugate, so the anti-triplet, which is this one here with the Dynkin label. This here is unique. So here it's the 1, 0, and this is the 0, 1. But for the dimensional name, it's usually you put an overbar, a bar over the complex conjugate representation, and you can even use that. You can even use that for entering the representation. But there are also unrelated representations which have the same dimension, and they are displayed by a prime. So here, for example, you have the 15 of SU3, which has the Dynkin label 2, 1. And you have a totally unrelated representation, which has the Dynkin label 4, 0. And then this is the dimensional name comes with a prime. Then for semi-simple or non-semi-simple Lie algebras like SU3 cross SU2 cross U1, like the standard model gauge group, for example, you use product IRAP, which is a collection of representation for the individual simple Lie groups that are in the semi-simple Lie group. So this here, for example, would be the 3 of SU3, the 2 of SU2, and a hypercharge of 1/3. And this is displayed in this manner. There's a Young tableau correspondence to SUN, only to SUN, and it works, and they can be displayed in LieART as well with the command Young tableau, working on the representation. Here I have a representation with the Dynkin labels 1, 2, 0, 1, and this is the output. So this is how the Young tableau for this representation looks like, and I can explain how this works. So if you have this Dynkin label 1, 2, 0, 1, you start from left and go to right, and then the first one here says the Young tableau on the right needs to have one box column, which is here on the right end. It has two box columns because of the 2 in the Dynkin label. It has 0 3-box columns. You don't see a column with 3 boxes. And it has 1 4-box column, which is the column here on the left. So it's very easy to construct a Young tableau. The weight system. The weight system of an IRAP is a collection of Weyl group orbits, which are already introduced, and they can be represented by a unique dominant weight. And orbits may be degenerated, so they have some multiplicity larger than 1, which needs to be computed. So to construct the weight system, you have the following steps. You determine the dominant weights of an IRAP, you compute their multiplicity, and then you generate the orbits and duplicate them according to the multiplicity of the dominant weight. So how does this work? The dominant weights are determined by subtracting positive roots starting from the highest weight, and the highest weight is the one that's here indicating the representation itself. So the highest weight is just 2, 1. The positive roots of SU3, there's a command for obtaining the positive roots, are these here. And now if you subtract the positive roots from the highest weight, you obtain these dominant weights, and we don't have the multiplicities of them yet. The multiplicities are computed with the command weight multiplicity, indicating the weight and the representation you want to know its multiplicity in, and they are computed with a improved version of the so-called Freudenthal recursion formula, which I'm not mentioning anymore here, or explaining it anymore. So this yields a list of the dominant weights of the representations and alongside with the multiplicities. And there's a command for obtaining this, which is dominant weight system. You get the dominant weights here on the left in the Dynkin label style, and on the right, you have their multiplicities. So now you just have to generate the weight system of the 2, 1 or the 15 of SU3 by generating the orbits out of the dominant weights. So this is the orbit of the first one, this is the orbit of the second one, this is the orbit of the third one, and the third one has a multiplicity of 2. So you have to replicate all of these weights here 2 times. So the weight system in the end will turn out like this, and you see, for example, this 1, 0 here appearing here and here. So 2 times, and you can go through the others as well, appearing 2 times. This is, for example, here and here 2 times, and the latter one is here and here, and everything else is just only appearing just once. For SU3, you can print the weight diagram in 2 dimensions, which is very nice property about the SU3. This here is the weight diagram of this representation 2, 1 that we just used. And you see this here in the middle with the rings. This is the orbit that has a multiplicity of 2, which is indicated by the rings. Then you have the second orbit, which are just the blue dots out here. And you have the third orbit, which are the lila dots out here. And now you see why the term orbit is very nice, because it forms like an orbit with the same distance from the origin for all of the orbits. This is the weight diagram for the decuplet, so the 10-dimensional representation of SU3. And I can put the weight diagram, I can put the Dynkin labels into manipulate, and then I can manipulate the Dynkin labels and have a plot of different weight diagrams. For example, if I increase the second Dynkin label, I obtain this here, which looks like a Christmas tree with a lot of colorful lights. And if I go back and use the first one, this is the inverse Christmas tree. And if I increase both of them, you see how the multiplicities add up, giving very nice plots. Tensor product decomposition. Tensor products appear very often, for example, in physics very often, for example, for the combination of angular momentum, so angular momentum with spin, for example, but they are also needed in particle physics for mass and interaction terms. The tensor product of irreps, they yield reducible representations, and that they need to be composed into direct sums of irreducible representations. So for example, if you have a tensor product of the triplet and the anti-triplet representation of SU3, the result is the direct product of the 8 plus 1 as irreducible representation. You can do that in LieART with the command decompose product and then indicating the 2 irreps, and the result is the right-hand side, the 1 plus 8. Instead of decompose product, you can also just multiply them, and LieART knows what to do. So in fact, high-dimensional irreps can be generated out of the so-called fundamental irreps of some Lie algebra. Sometimes it's called generating irreps because they generate the high-dimensional irreps. And the 3 and the 3 bar of SU3 are, for example, fundamental irreps. So the method for tensor product decomposition is shown here in these graphs. So this is the weight system. On the left, this is the weight system of the triplet. Then you have the weight system of the anti-triplet, and you just take the weight system of the anti-triplet, which results in this results in this here. Well, it tells me that my internet connection is unstable. I hope you can still hear me and see me. So it results in this here, and you can see how there are some returns to the origin. So it turns out that this is a reducible representation with this outer orbit, and you have the zero weights here with a threefold degeneracy. And then you have knowledge about the representations in SU3, and you know that there's an 8 and there's a singlet, and then you can decompose these weights into these representation. How does this work in LieART? So let's take the weight system of the triplet, which is this here. Let's take the anti-triplet, and then we build this outer product here, which is indicated here, by just using outer from Mathematica, and have these weight products. So this is the result of that. Now we only take the dominant weights because working with the dominant weights is much easier to do than with all of the weights, and it simplifies the algorithms a lot. And we obtain the dominant weights of all of these weights. Here is the 1, 1 and the 0, 0, and they come with multiplicities of 1 and 3. You see the 0, 0 appears here, here, and here, so in total 3 times. Then you sort out the containing representations recursively using the knowledge about the weight system. So this is the dominant weight system of the 8 with the same dominant weights, but different multiplicities. So it's not a, here it was a 3, here it is a 2. So you can in fact subtract it and sort it out. There's even a command in LieART, which is called sort out. And then you're only left with the singlet here, and you can then sort it out, giving you the singlet. And then with reap and so, you can get the 8 and the 1, and that's the result of everything. Well, in LieART, this was implemented in the very first version of LieART, but then for big representation, it turned out that this procedure is quite slow. So it was much easier. It was very slow, and then I looked into the problem and I found that there's a different way, and now I implemented a different, slightly different algorithm based on so-called Klimik's formula, which does some shortcuts at some points, and this is done for performance reasons because this is much faster. For SUN tensor products, however, there's even a faster method. You can use, if you're decomposing tensor products in SUN and doing this by hand, you might have learned something about Young tableaus and how to bump boxes with Young tableaus to do a decomposition of a tensor product. And I implemented that in LieART as well, and it turned out that this is even faster for SUN than using Klimik's formula. So this is automatically used. You don't need to know which kind of algorithm is used. It's done all automatically. Okay. Here are some examples. Decompose the tensor product of the 3 times 3 times 3 of SU3. So decompose product can also, you can have more than 2 arguments, and it will just apply it appropriately internally. Result in having this result. So it has the 8 and it has the 10. Then decompose the tensor product of the 8 times 8 of SU3, so the adjoint representation, which gives you this result here. Because it's 2 times the same representation, you can also use power, and like with times, LieART knows what to do. And internally, this sum here with multiplicities, for example here, is represented by IRAP plus and IRAP times. You can see that here with from the input form. This is very nice to know if you need to process it any further. If you need some other form, you can transform it to a list of IRAPs. The same way for further processing, just say IRAP list, and it will list all the IRAPs and even resolve the multiplicities. So the 8 is appearing here 2 times. Here's another example, the tensor product of 4 IRAPs, but now this time of SU4, yielding this result down here, which is a little bit more complicated. Subalgebra decomposition. Subalgebra decomposition is used in particle physics due to spontaneous symmetry breaking, and it's also used in, especially used in grand unified theory theories, because you have the standard model gauge group, which I mentioned earlier, and it's a non-semi-simple Lie algebra, and you try to put that into a simpler group, into a higher group, but which is simple. And then you break everything down to the standard model gauge group. LieART can decompose in IRAP into a so-called maximal subalgebra. And it uses projection matrices for that. For some, it needs the projection matrices built in, but for some, it can derive the projection matrices. So here's an example how to decompose the 10 of SU5 to the subalgebra SU3 cross SU2 cross U1, which is the standard model gauge group, because it's so popular and it's used in physics a lot. We first save the target subalgebra here. Then we apply the respective projection matrix. There's a command for that, projection matrix, SU5 as the origin algebra, and here product algebra SU2 cross SU3 cross SU2 cross U1 as the target algebra. And this is the projection matrices. Then you take all the weights of the 10 of SU5. This is the weight system here of the 10 of SU5. And then you apply the projection matrix to each of the weights, which gives you this relation here. You see this is one of the weights of SU5. And this comes out of the projection when you apply the projection matrix. In fact, since there's only one here, this here is selecting the second column of the projection matrix, 0, 1, 0, 4. And then you divide this up. You group it by the target algebras. So this here is the Dynkin label for a representation in SU3. This is a Dynkin label for the SU2, and this is the U1 charge. Then again, you keep only the dominant weights, which looks like this here. So for the SU2 part is here, SU3 part, this is the SU2 part, and this is the U1 charge. And then you're sorting out product IRAPs like we did for the tensor product. And then you end up here with this result here. And if you show this in the standard form, giving you the Dynkin labels, you can even see, you can even recover the dominant weights that we saw here. For example, let's highlight this one here. This is the SU3 representation. This is the SU2 representation. This is U1 charge. And you see it right here. This is just the first row here in the dominant weights. So branching rules on maximal subalgebra. There's a mechanism in LieART to identify the maximal subalgebras of algebras. And there are three types of subalgebras: regular semisimple, regular non-semisimple, and special subalgebras. So a simple algebra would be just something like SU3. A semisimple subalgebra is this product like SU2, SU3 cross SU2. And a non-semisimple has an additional U1 factor. So the standard model gauge group is a non-semisimple Lie algebra. So for non-semisimple algebras, you get the subalgebra by removing a dot from the Dynkin diagram, which becomes the U1 charge. So I have a picture of that here. You have the SU5 on the left side, you have the Dynkin diagram, and we just drop the third dot, which stands for the third simple root. And then we have disconnected Dynkin diagrams. The first one here stands for the SU3. The last single dot for the generator for the simple root of SU2. And the third dot becomes the U1 charge. Well, the dropping a simple root from the Dynkin label means just dropping the individual Dynkin labels. So the third one in this way here. So the U1 charge is now the coefficient and the weights linear combination of simple roots. I said that weights are linear combinations of simple roots, and just the coefficient for a weight with respect to the third simple root. This is the U1 charge, and usually it's some fraction. So here, for example, I have these coefficients for the whole weight system, and this would be the third one. It's 4/5, and then you just multiply it, you normalize it to being an integer. This is where the 4 comes from. So, and then you can, for determining the projection matrix, you have this equation here. So P is the projection matrix, W is the matrix of the weights of the 10, which is unprojected, the unprojected IRAP, and this W prime here is the projected weights, and then you can arrange this in the way with the U1 charge as I did here. So you move the U1 charge to the end, and then you can solve this equation and you obtain the projection matrix. You can do that for one representation, and then you have a projection matrix which you can use for all the other representations in the same branching from SU5 to SU2 cross SU3 cross SU2 cross U1. They're semi-simple subalgebras, so they don't have this U1 generator. And then you cannot drop a root, because then you would obtain a U1 charge. Instead, you're using the so-called extended Dynkin diagram. The extended Dynkin diagram, those are the diagrams that were shown at the beginning of the talk. So the very first slide before I was talking to you had the extended Dynkin diagrams in the background. Here you add the most negative root to the set of simple roots. For SU6, the Dynkin diagrams is just the row below here, and the most negative root is here indicated by a minus gamma here. So this is the extended Dynkin diagram for SU6. And these are the Dynkin diagrams for all the other LieArT. And then it works the same way as I just described for the semi-simple, for the non-semi-simple LieArT. There are also special subalgebras. They come with a very special embedding, and you cannot really derive them from the root system, and they need to be determined for every algebra, subalgebra individually. There are a lot of projection matrices found in literature, and you can just put them into LieArT, and we did that for up to the rank of 15. That was the major accomplishment of Robert Saskowski, who did this work. It's just one line here, but this is really, believe me, this is really a lot of work to do that. And we had even to modify some of the commands in LieArT, because some of the special subalgebra branchings have multiple branchings. So there are different ways of embeddings. For example, E7 to SU2, there are 2 or even 3, and you need to know which one you use. So if you use decompose IRAP, then you have a new argument. You have an argument in the end where you indicate which kind of embedding you want, if it's the first one or the second one indicated here. So the results can be very different. Here I have some branching rules examples, how to decompose the 16 of SU10 to SU5 cross U1. This is also very popular in grand unified theories, using SO10 and especially the 16, because the 16 turns out to be, if you go to SU5, this can represent one family of the standard model. And then you have a right-handed neutrino here, for example, in this representation. Here's how to decompose the 27 of E6 to SU3 cross SU3 cross SU3, which is this here. And this here is a more complicated example. So we have a product IRAP, which is here the 24 of SU5, the 3 of SU3, and a U1 charge, which is already there. And now we want to decompose here just the 3, so the SU3 to SU2, which generates a new 1 charge. So you can do it by decompose IRAP using here the product algebra, and then indicate with the same index that we used for the special embedding. You are saying that you want to apply it to the second position, which is here. So this is the result. So the 3 decomposes into the 2 of SU2 and the 1 of SU2, and this is the new U1 charge that comes along with the already existing U1 charge. This here is an example for branching rules for all totally antisymmetric IRAPs, which are also called basic IRAPs of SU6 to SU3 cross SU3 cross U1 in a table form, and I use the LieART command IRAP rule, which gives you this nice looking way of describing the branching rule, which is the usual way how it is displayed in textbooks. So that's about it. If you want to have more information about LieART, you can go to LieART Project Home on HepForge for downloading it. There are the installation instructions, and there are links to the papers and everything else. And there's also a post about LieART in the Wolfram community. This is the link to this post. And LieART is connected to these two publications from 2015 and 2020. From the ePrint here, you see the initial annunciation on the archive is from 2012. And then this is the paper about LieART 2.0, which is from 2020. So thank you very much for your attention. And well, I'm very happy to take questions, but so far I only see one question here. There's someone who just asked for the notebook that I'm presenting here. And I just talked to Karen, and I will give her the notebook, and she will upload it, and we'll put a link into the YouTube channel. So any other questions? So let's wait a few seconds. Your questions need to be transferred from the chat in YouTube to the chat window that I have here. But so far, I cannot see any more questions. Oh, okay. There's one question. From YouTube, Jose, can you comment on the possible connections to other systems? I don't really know what you mean by other systems. Do you mean other systems outside of Mathematica, or? Oh, okay. Tensor computations, Feynman diagrams computations, and so on. Well, you have seen the output. For example, here I made some. Oh, someone said, thanks for the talk. So you see here, most of you, if you're using LieART, you will probably use the tensor product decomposition and the subalgebra decomposition. And I think this is the most important part here, that the output comes in this way here, IRAP plus, IRAP times, and then you can take this output and use it as you want in any other system. Or you can use this IRAP list. Sometimes this is even nicer to use than IRAP plus and IRAP times. But of course, if you have high multiplicities, this is very inconvenient, because then you have a lot of replication of the same representations, which is probably not the best way to use that. There was I had a slide in here about a LaTeX package that comes with LieART. You can output the results of such a decomposition here, for example, in LaTeX style. Let me try this here. So this here is the result, and if I say LaTeX form, it will give you this here. So you see here commands like IRAP or IRAP bar, for example, and you can take this and copy it into a publication, for example, and then include the LaTeX package that comes with LieART, and it will understand what this IRAP and IRAP bar means, and it will display it just as it was displayed here. So the bar is properly this is then probably done in LaTeX. So if you have a very complicated output, for example, this is very nice to use, because you don't really want to type a very complicated output. Like, let's say you have here this to 5, or let's even say 10 this might take a time until this is finished. Let's see how long it takes. There's another question. Is there a direct correspondence to well-known particle properties if one, for example, wants to explain all particle physics in a given era? Well, yes, in a sense. For example, the hypercharge. The hypercharge is, let me change this here to 8. The hypercharge, for example, you can get the charge of a particle from the hypercharge. This is, for example, one property that you can pull out, or you can pull out the properties if you decompose it to the standard model gauge group, and then you will see where weights appear in the standard model and can derive a lot of the properties from there. I hope that answers your question. No, 8 is even too long, or I have to abort the other computation. Let me abort this. Let's take 7. Yeah, that works. Okay, any other questions? So if you don't have LieART there's one more question. Is there a connection between Lie algebras and lattices? Probably there is, because there's a lot about symmetries and discrete symmetries in lattices. There might be, but actually I don't know. I used it for particle physics, so that's the world I was living in using Lie algebras. And I was in fact doing unified group theory. Okay, or semi-lattices, he's asking. No, actually, I don't know. I can't answer this question. I'm very sorry. So I was doing grand unified theories, and for doing that, I needed something that is doing representations and especially tensor products, because you need the tensor products for mass terms and interaction terms in the Lagrangian. And in fact, you need to find out if there's a singlet in the decomposition, because then you can put it into the Lagrangian, because the Lagrangian needs to be a singlet with respect to all the Lie algebras that appear there. So this is one thing that I needed, and then what I already mentioned is you need the subalgebra decomposition to see if the standard model gauge group is contained in some algebra that you think is the right unifying algebra, or if you have some extra particles. Of course, you don't want to have some extra particles which are not measured. There are some ways of just saying, well, they're super heavy, for example, and then you can integrate them out. But this is a big topic, grand unified theories. And in doing grand unified theories, I built up this, it was only about SUNs. In fact, it was, I did an SU9 and SU12 model. And it turned out when I built LieART, or the tools that became LieART later on, it turned out that a lot of things that you do for SUN, you can even translate to all the other Lie algebras. So that's why I built LieART in general. And then it was later on extended by Robert Saskowski and Tom Keppert. He taught me a lot about Lie algebras and how this works. And he tested LieART at very much length. And we also discussed the interface, because I think the most important thing for software is a nice interface, an easy to use interface. And I hope we succeeded in doing an easy, accessible interface for LieART, because it's, well, it's a very complicated topic. So at least the interface should be easy. Good. Any more questions? I think we still have a few minutes. Okay. I don't see any more questions. Okay, there's another questions. So Dan Mossinson, Michael Dan Mossinson says, seems useful for indexing of storage. It seems perhaps for AI LMMS. Okay. Well, maybe. Thank you for this comment. There's another question by Nick Mozin. Would be cool to have examples of producing particle tables like first generations of fermions in SU3 computed with the Packlet. Would be very educational. Thank you. Well, for the representations of SU3 and a lot of other LieAlgebras, we have extensive tables in the publications. So the publications are very big. They're like a phone book. So I think they have more than 200 pages because we included a lot of tables with properties of IRAPs, with tensor products, and with subalgebra branching. So if you can't use LieART or Mathematica, for example, you can even look up a lot of information about that. And of course, you can find a lot of information about particles in there because the properties of IRAPs then or of weights they refer to particles. So particles are then a state in um, in the uh, in the Hilbert space that the Lie algebra acts on. Okay. So any further questions? Okay. There's no other question coming in. Um, so thank you very much for listening to me, and thank you very much for the interesting questions. And I hope you enjoyed this Wolfram R&D Live. And then I hope to see you or meet you soon. So all the best. See you soon.